Okay, so we had just demystified the Eddington limit. So first of all, accretion disks. Models of accretion rate, both above and significantly below the Eddington luminosity, have been developed over the years. And you can see that when you allow for the symmetry to be an accretion disk, and then you add magnetic fields, you had GRMHT simulations, then you see that you can find stable solutions also above the Eddington rate. The accretion disk changes shape, so at slightly below Eddington luminosities, we have thin disks, the typical Shakura-Sunyaev solution. I will touch on it if I have time, probably not, but you can find it in the note. At very low accretion rates and very high accretion rates, the disk really changes structure. It becomes thicker, and usually you have the production of jets. So super-Eddington accretion is not a myth. But also another point that I think is important to note is that the Eddington limit in spherical symmetry and everything usually assumes hydrogen only, so the Thomson cross-section. Interesting things happen with dust. Andy Fabian has done a lot on this. Andrea has applied this to dust in galaxies, and I looked at this for AGN littoral dots in a recent paper. It's just a way, for instance, to get rid of the hot dust, which is one of the problems for littoral dots. If you have questions on this, we can discuss in a minute. First, I want to continue on super-Eddington. So this is something that we were discussing at coffee. Super-Eddington accretion does not imply super-Eddington luminosities. Sorry. This is because when you have super-Eddington accretion, you have a lot of mass in a small region, so you have very high densities. This was all work developed by Mitch Bigelman in the 70s. You produce photons in the disk, but the time for photons to leave the disk is longer than the time it takes for photons to actually be advected in the disk. So the photons are unable. So think of photons leaving the sun. They are produced in the center of the star, and then they have to get out. It takes a long time. This is at the extreme. The photons never have time to get out. So this means that you can accrete a lot of mass, but you don't produce a lot of photons. In some way, you can think this as a low radiative efficiency in the conversion of mass into radiation. Caveats. I will stress a few caveats here now. I mean, again, super-Eddington accretion. It's something that if you wrote papers on super-Eddington accretion until 2023, it's one of those other cases in which you had trouble. I have some interesting reports. I could read from the reports about how crazy or stupid these ideas were. If you started recently, you probably have heard super-Eddington accretion as, oh, well, of course, all the AGN at higher airshift is super-Eddington. Now, although I've been a supporter of super-Eddington accretion for many years, I want to stress some caveats and the reasons why we should not just easily accept this as the solution for everything. One problem is it's unclear how low this radiative efficiency is. So, for instance, simulations by Zhang et al. In 2019 find that convection in the disk can actually counteract this trapping of radiation. Super-Eddington accretion can also produce powerful jets and winds that push gas away. This means that the time you can be in super-Eddington phase can be extremely low. But this can be counteracted by by deep potential wells. So this figure just shows the ratio of luminosity over the Eddington luminosity as a function of the accretion rate. These dashed lines is what you expect if you don't modify the radiative efficiency for trapping. And this is an analytical model suggesting this trapping. But then you see here results from various simulation, generativistic simulation, which, and as you can see, they don't converge to either of the two limits. So I think that this is still something to be seen. In principle, if you have super-Hydron accretion, you have what I say, more bang for your buck, meaning that short phases of super-Eddington accretion can grow the black hole more than prolonged phase at Eddington limit. This is shown very nicely in this paper, where you see the growth of black holes with Eddington limited and super-Eddington radiation. And even if you have that for the most time, the accretion is sub-Eddington, these short super-Eddington phases can grow the black hole more. Big, big, big caveat. These simulations assume that the accretion rate that you have at the edge of the accretion disk, actually, no, these are cosmological simulations, so the accretion rate that you have at hundreds of parsecs is the same that happens at the innermost stable circular orbit on the black hole. Models of super-Eddington accretion, in particular the ADIOS model developed again by Mitch Bigelman and Roger Blanford, find that within the disk there are significant mass losses, winds. So basically the photons can eject mass from the disk, which limits the accretion rate on the black hole to, guess what? The Eddington limit. So we have done all this work to increase the accretion rate, but it doesn't work. So there are recent simulations. There is the first simulation, Chris Fragile and collaborators, this is this year, that using initial conditions different from all previous, so these simulations here were all initialized with some type of initial conditions. So Chris Fragile and collaborators have changed the initial conditions and found a solution that is similar to this ADIOS model, or ADIOS, I don't know how they pronounce it, meaning that you can have super-Eddington accretion at the edge of the disk, but what goes into the black hole is limited to the Eddington accretion rate. So not helping black holes to grow more. This is, as I said, work in progress, although I mean, the models, the ADIOS models date back to the 80s. Okay. Now, a few massive black hole growth in general. So we have discussed the ways black holes can grow by accreting gas, merging with other black holes. I haven't touched yet on accretion of stars. But on top of this, we have to think also of other processes. The famous AGN feedback. As we know, AGN feedback, not AGN radiation, not the AGN feedback, was invented in order to match the galaxy mass function. And it was calibrated on simulations that were meant to reproduce the galaxy mass function. But something that we have to remember is that AGN feedback not only regulates star formation, but it also very good at regulating black hole growth as well. So this is a bit of an extreme case. This is for super-Eddington radiation, but although it's a bit extreme, it shows you what happens. The moment the black hole starts injecting high amounts of energy, what you have is a drop in the density of the gas. You carve holes in the gas or you displace it, and an increase in temperature. Now, since typically in models we use the Bondi-Hoyle-Littleton accretion rate, so the black hole accretion rate is proportional to the black hole mass squared, the mean density, the density, sound speed, and relative velocity of the gas with respect to the black hole. If you decrease the density by orders of magnitude, if you increase the temperature, which determines the sound speed, all of a sudden this accretion rate drops significantly. And this happens on scales that are basically, I mean, when black holes dump their energy, they dump their energy near themselves. So this happens before any effect on star formation happens. So, for instance, in these simulations, one is, the orange one is stronger than the purple one. the black hole growth is significantly different. The star formation history of the galaxies is pretty much identical. So AGN feedback acts on the black hole before it acts on the galaxy. Sorry, this is a bit ugly. Much better. Now, besides AGN feedback, something else that is very damaging to the growth of black holes are supernovae explosion, also known as supernova feedback. So these are just two simulations, one with supernovae and no AGN feedback, the other one with AGN feedback but no supernovae. This is the gas mass. You can think of it as the available fuel for the black holes on small scales, 20 parsecs, very close to the black hole, and this is on galaxy scales. You see that if you have supernovae, the gas density shown in black has very large variation. Basically, every time a supernova explodes, you create a bubble that is a few parsecs in scales. And so the available mass in a small region can be very much subject to these type of fluctuations. As I said, one supernova does a lot of damage in 20 parsecs. AGN feedback does not have the same result. So what we had found for many years, and with very different accretion recipes, with very different supernova feedback, very different AGN feedback, is that consistently we found that supernova feedback suppresses the growth of black holes in low mass galaxies. When I say low mass galaxies, this is because you can just consider this an energetic argument. You can compare either the expansion of the supernova bubble with the escape speed from the galaxy center, or you can do an energetic or entropy argument. These are different models assume different assumptions, and you always find that above about 10 to the 10 solar masses, the potential well is sufficiently large to counteract the growth of black holes. Since this is dependent on the local potential well, the presence of nuclear star clusters, we have already mentioned nuclear star clusters as a kind of an incubator for black hole formation, but they also could help the growth of black holes because since they are very dense stellar structures, they deepen locally the potential well. So if the black hole is at the center of the nuclear star cluster, all this effect of supernova feedback or supernova explosions really is much reduced. This is work by Christian Parkman just last year, showing that in the presence, so with or without a nuclear star cluster, focus here on the orange case, for instance, the growth of black hole is significantly different. Note, however, that once the black hole mass is close to the mass of the nuclear star cluster, so we get to the 10 to the 5 solar mass case, it doesn't matter anymore. So this is still in flux. That's why I put the question mark there. But at the moment, a significant problem that we're having really is about growing black holes in small galaxies or in dwarf galaxies. Dwarf galaxies don't grow much themselves. I mean, if we observe at low redshift a low mass galaxy, it cannot have been much more massive before, the opposite. And so actually something that this implies is that their massive black holes also cannot grow much statistically. In other words, if I see a black hole of 10 to the 5 solar masses at threshold 0, it must have not been much smaller black hole before. So in other words, if I still see low mass black holes in low mass galaxies today, it means that in those low mass galaxies, black hole growth cannot have been very efficient over time. And in fact, you can prove, this is something, I like this paper because it's fully analytical. You can show that if the growth of black holes in low mass galaxies is generally efficient, you overpredict the luminosity function of AGN at the faint end. This is at redshift 4, it's the same at redshift 3. So this paper, for instance, was showing a stellar mass, a critical stellar mass of more than 10 to 10 solar masses, below which you have to suppress black hole growth in order to match the luminosity function, the faint end of the luminosity function at redshift 3 to 4. Now, this is completely the opposite of I'm sorry, and you can, and this in simulations find it exactly the same. Now, this is obviously the exact opposite of what we're seeing with JWST. Roberto has shown you cases of black holes of mass 10 to the 7 solar masses in galaxies 10 to the 7, 10 to the 8 solar masses. So if this observational result is true, it implies that there is a clear transition in the accretion properties at redshift less than 4. Otherwise, we would overestimate the faint end of the luminosity function. The other option is that we are missing still AGN, a significant fraction of AGN, at redshift 3 to 2, all the way to 0. So what I keep on asking people is, can we please stop looking at crazy black holes at redshift 10, 11, and look at the AGN luminosity function at redshift 3. I think this is both the faint and the bright end at lower redshift are dependent on the properties at high redshift. So really making sure that we have a full demography at lower redshift, again, lower redshift 3 or so, is very important to calibrate models and so on. Okay, now we have all the ingredients. And I just want to touch a little bit on the other two processes, in particular mergers between black holes and accretion of stars, which in terms of observations will be gravitational waves and tidal disruption events. I will start with gravitational waves. You all must have heard about LIGO detecting black holes in 2015. We just had the anniversary. Now there is Virgo and Kagra also have joined the effort. These are what, for me, are high-frequency detectors. And pulsar timing arrays and LISA, which is a space telescope, will go to lower frequencies. Now, the frequency of gravitational waves emitted when two compact objects merge is inversely proportional to the mass of the compact objects. So if LVK at about Hertz frequency detects stellar mass black holes, when you go to nanohertz frequencies, you have black holes of mass 10 to the 9 solar masses or so. And in the millihertz regime, you will have black holes with mass about 1 million solar masses. So really, gravitational wave detectors work in the same way as telescopes. If you want to observe radio, you have to build a type of telescope. If you want to observe X-rays, what you build is very different. So the way I consider gravitational wave detectors, being an astrophysicist, is really as having 3 different telescopes for gravitational waves. Now I will stop talking about LVK because I'm focusing on massive black holes. But why are gravitational waves so important or interesting here? Because when we look at the growth of black holes over time, so here you have redshift time and this is black hole mass, theoretical models predict that black holes form small and then they grow over time by merging with other black holes. Each of these dots is a merger and the smooth accretion of gas. So really what we can, when we use a joint combination of electromagnetic information and gravitational waves, we can characterize the combination of these two processes. Now, besides this generic statement that black holes grow with galaxies, if we focus specifically on pulsar timing arrays and LISA, if you want to know more about the instruments themselves, let me know, but I'm not going to touch on how they were built, were built, and how they work. But as I said, pulsar timing arrays, nanohertz frequencies, black holes with mass larger than about 7.5, a few times 10 to the 7 solar masses at redshift less than 2. These blue contours, the light blues, they show the reach in terms of signal-to-noise ratio of LISA. So basically, you can detect black holes with mass about 10 to the 5 solar masses at redshift 20 and beyond. In fact, when you compare this with what our telescopes can do, LISA has a much deeper reach into lower black holes at high redshift. But if we want to study black hole mergers, we have to understand black hole mergers, or at least the physics of black hole mergers. And this is really a fascinating topic. It started in 1980 with a paper by, guess again, Bigelman, Blandford, and Rees, in which they first look at just what happens if two galaxies have massive black holes, they merge. Do the black holes merge? This is the question, and the answer is not always. Galaxy mergers may lead to black hole mergers, but not necessarily. So basically what they focused was then on a merger of two galaxies and then the phase all the way to gravitational wave emission. Now what we have added to that is cosmology. So if we want to understand the merger rate of black holes and how this connects to black hole growth and electromagnetic radiation, so AGN, what we actually have to do is to simulate a large patch of the universe, to have a statistical sample of galaxies, look at galaxy mergers, in which each galaxy hosts at least one black hole. Once the galaxies have merged, then follow the dynamics of these two black holes down on small scales until they form a binary. The binary formation happens at about parsec scales. For me, a binary means that the two black holes are energetically bound. And then on milli to microparsec scales, the two black holes start emitting gravitational waves. Well, technically they emit gravitational waves all the time, but gravitational waves emission becomes efficient and drives the black holes to coalescence on these scales. You know, hundreds of megaparsecs down to milliparsec. This is obviously not doable. So what we typically do is to separate the problem into different bits and then compare them. As I mentioned, the merger of black holes is not a given. If two galaxies merge, it's not necessarily true that black holes merge. This was the concept for this slide is from Monica Colpi, who among the various things that she worked on is black hole dynamics. The evolution of the separation of black holes as a function of time is highly uncertain. The reason is that you have lots of physical processes that interplay one with the other, which depend on the properties of the host galaxies and the black holes. Back in the 80s, we thought, well, I was not working yet, but I was alive. We thought that the bottleneck was at about parsec scale, the so-called last parsec problem. Now the bottleneck appears to be on kiloparsec scales. And this is because up until a few years ago, about 5 years ago, all our models assume that galaxies have a smooth potential. And we use analytical approximations. Typical case is dynamical friction on Binet remain. This is just the equation from the textbook, in which if you assume that your galaxy is an isothermal sphere, we love isothermal spheres, then the black hole would, and the black hole is in a circular orbit, it would slowly spiral in on this time scale that you can integrate exactly. But when we go to high-redshift galaxies or dwarf galaxies, the potential is usually not described or describable with a smooth potential. We have seen pictures of high-redshift galaxies. You have clumps, you have shallow potential wells, in particular really shallow potential wells. So you have, there is no point in the galaxy that acts as a global attractor. So black holes just move around, just to wherever they feel a little bit of strength force, but not in a predictable way. So it's what we call an erratic dynamics of black holes in high-redshift galaxies. It can be mitigated, again, by a massive black hole. So here the case is a higher mass black hole, shown in red, has a less dramatic fluctuations than a low mass black hole. I mean, you can think it's actually very, very simple. You have a distribution of stars and black holes. If the black hole that you care about has a mass similar to the other stars and black holes, it's just moving in a distribution of objects that are like itself. in order to dominate the potential, in order to have a strong force, dynamical friction, so the black hole has to dominate the potential in its local environment. So a way to make this more effective, for instance, again, to invoke star clusters. If your black hole is surrounded by a nuclear star cluster or a star cluster because it was born there or because the star cluster was born around the black hole, the dynamical evolution becomes much cleaner. So this is the case without nuclear star cluster, and this is the case with nuclear star cluster. Actually, the effects are more, it's not only the mass by itself, but it's that the stars in the star cluster itself provide a self-force that allow the black holes to have an enhanced local potential. So this is something that we have been hoping for. But in the cases where dynamic is inefficient, like in this case, or in this case, the black holes will not reach the galaxy center, like ever. And in fact, I mean, we have been predicting since 1994 the existence of off-center wandering black holes in galaxies at all redshifts. This is from the obelisk cosmological simulation at redshift 7. We already have a galaxy with 1, 2, 3, 4 black holes, 1 in the center and 3 offset. And as Roberto has also shown, now we start seeing some hints of this also in observations. So the expectation has always been that black hole dynamics is not necessarily effective, and you would have stranded black holes in various galaxies. And I know if you have more questions, we can talk about this later. Okay, before moving to TDEs, actually, no, let's stop a few minutes for questions. Yes?
I have a question about the time scale of gravitational waves.
Yes.
If the time scale is very short, it might be very difficult to observe.
Well, yes. Okay, so the time scale depends on the mass of the black holes, the mass ratio of the black holes, and the separation of the black holes. It depends as the separation to the power of 4, it's very rapid. And in fact, for gravitational wave emission, for supermassive, already for LBK, the larger the black hole mass, the shorter the time scale. I don't remember now the exact power, but it's a strong power. And so that's why the highest signal-to-noise ratio events in LBK are also the shortest. For black holes, it's a bit different. Sorry, for massive black holes. Because, especially in LISA, hopefully I will show this, the black holes enter the sensitivity of LISA, I mean, black holes in the right mass range, months before merger. So you can accumulate a signal-to-noise ratio. But this depends significantly on the mass of the black holes. So since we have seen that the frequency is inversely proportional to the mass, the most massive black holes spend a very little time in band, and then we are in that situation. So usually when we characterize the masses detectable by a detector, we take these into account. So for instance, LISA can see black holes with mass 10 to the 8 barely, so we usually say 10 to the 7 or so. But it depends significantly on the black hole mass. Yes?
Yes, I have a question about the dynamic friction.
Yeah.
If I remember correctly, the greatest from Lilly was for, let's say, a minor merger, because during the merger all the gas is probably not made an isothermal approximation, but if you have a minor merger. Are there any kind of, let's say, correction to this formula for major merger? Because I think we are interested in studying major merger to go to see.
Yeah, so this is a subtle question. So in reality, the equation that I showed doesn't assume any merger. You have an isothermal sphere, and you have a black hole going in a completely unperturbed environment. Now, an interesting effect that happens in galaxy evolution is that for magical reasons, well, not totally magical, but kind of, the time for galaxies to merge is very well approximated by the time scale for dynamical friction. This work done by, the analytical work was done by Monica Colpi 2000 or so, linear response theory. And so if you approximate the time for a merger with dynamical friction, then what you can do, and this is what Quinn and Yu has done in the early 2000s, is say, okay, up to which point I approximate the evolution just with the galaxy merger, and at which point do we have to switch to a black hole? So what you can show is that in minor merger in particular, the small galaxy is stripped until, again, I'm simplifying this a bit, until you can imagine it is stripped so much that the black hole is naked. So in some sense, you have to modify the mass of the perturber, the object that is infalling over time. So for major mergers, this is a bit simpler, actually, because you consider the dynamical friction time scale for the time scale of the two galaxies merging. And then the black holes are, in simulation, that's what we are so close that you can just move to the hardening phase or the evolution of the binary. So you expect that in major mergers, basically, you don't necessarily have to use the time scale for the black holes, but for the galaxies themselves. As I said, it's more, but then it depends. There is a paper by Michael Tremmel, 2017, showing how this depends not only on the mass ratio of the merger, but also on the density profile. If you have a shallower density profile, stripping is stronger. And also it depends on the orbital parameters. So, yeah, but in principle, one could find some scale relations. The other point, and I haven't discussed this much, is the effect of bars and global torques that, depending on the position of the black hole with respect to the forming bar, it can be dragged to the center or outside. So in most models now, these are introduced as stochastic events with a probability distribution function for the time to happen. Yes?
So you mentioned the off-center black holes, the wandering black holes, that they are predicted by simulation.
Yep.
Do we also observe them? And, the number densities similar to what we predict?
Sorry,
So
the number.
Are the number densities similar to what?
Well, from the observational point of view, so the work that Roberto has shown, this is at high redshift. Before that, we only had low redshift cases. For the most part, they've always been candidates. Usually they are low, so from simulations, what we typically have is that the mass of the wandering black holes is lower than the mass of the central black hole. I mean, it's obvious. These haven't been able to find a position where to grow. So for instance, if you think of the Milky Way, for instance, you predict black holes that are 10 to the 4, 10 to the 5 solar masses or less, which means that it's very hard to see them. So if you actually calculate the probability of detecting wandering black holes by their emission, is extremely low. So yes, we're totally in agreement with observations. Specifically for the Milky Way, there was a case, a thing very close to the galactic center that was either considered an intermediate mass black hole, very close to the center but not merging, or a star-forming cloud. So this has been, but so I would say that at the moment we're still consistent, mainly because it's extremely hard to see these wandering black holes. Now with JWST using IFUs, they're finding them. We have had candidates for years. If you cannot measure and prove that they are black holes, that's the key problem. Anything else? Yes?
So my question is, do these wandering black holes only occur after matter mergers, or because as far as I know, when dark matter halo mergers, if they are in the matter mergers, the mass ratio would be high, and the satellite halo would be tidally stripped. And if one black hole in the center of the satellite halo, it would be it cannot be go into the center of the primary halo. So my question is, do these wandering
Yeah, no, so, okay. If they're mainly generated by minor mergers, is this the question? Yes. In principle, yes. What you said is all fully correct, except that if you already have a wandering black hole in a galaxy and you have a major merger between this galaxy and another galaxy, the wandering black hole will be a wandering black hole in the newly formed galaxy, although it was dragged into the galaxy by major merger. So you have an accumulation of wandering black holes over time. In other words, a wandering black hole will remain a wandering black hole even after a major merger. So it's true that they're mainly generated by minor mergers, but then it depends how you define their actual origin. But yes, your intuition is correct. Yes?
I'm wondering about what are the fates possible for those black holes?
Typically, nothing. So they just stay there forever. So when you see an off-center black hole, it can be a wandering black hole. For me, a wandering black hole is really a black hole that is unable to do anything. It's stranded there. It doesn't have enough mass to go to the center. But then an off-center black hole can also be a black hole on the way to merger. You know, it doesn't have a sign saying I'm going in or not. And then it can also be ejected from three-body interactions or gravitational recoil. So something that we looked at recently, just because it was my curiosity, was in a simulation, we actually have all of these kinds. Can we see if there is some specific difference? My naive expectation was, well, if I have an ejected black hole, it's ejected on a radial orbit. If I have a wandering black hole, it's typically on a kind of circular-ish orbit. Fortunately, since the galaxies are not smooth potentials, the eccentricity of the orbit evolves with time. And very quickly, the radial orbit is, well, not radial anymore. It's eccentric, so with a similar eccentricity as the other ones. So we have a variety of off-center black holes that could be different things. Typically, again from simulations, what we see is that off-center black holes that are active, so can be defined as off-center AGN or dual AGN if there is another one. The higher the luminosity of the off-center black hole, the more likely it is that it's going to the center. Why? Because if it has a high luminosity, it means that it's surrounded by dense gas. It's increasing its mass. It's making the dynamical evolution faster. But the low luminosity ones, nothing going to happen. Yes? Yes.
Black hole to go into the center of the potential. So how this evolves?
Yeah, okay. So first there are two communities, the semi-analytical models and simulations. I started with semi-analytical models, so I knew that it was just an integral of an equation, so I trusted their solution there. And still in the semi-analytical models, you have the same problem. So with simulations, mainly what we have now is the no smoothness of the potential. So I would say that even very high resolution simulations, those that include dynamical friction and so on and so forth, they still have these wandering black holes. And again, since you can, perhaps I'm biased, but since you can show analytically that this should happen, I kind of trust it.
Well, yeah, that was my feeling, but that's what I don't understand. Some people just would continue to because they think it's a numerical.
That was just, I mean, if I think of, this was like 2006 or 7. In a conversation, there was Michael Tremmel, who was the first person to implement the dynamical friction force in simulations. He was giving a talk showing how difficult it was. And a very famous person in the audience said, of course, you pin black holes. It's stupid to think that you can follow the dynamics. But he succeeded. It is very difficult. I mean, I worked on... So what was it? I worked on Chang'e, no, first on gasoline, Chang'e, Ramses, and Gizmo on the same problem. Black holes don't stay still. Ramses is the worst, by the way. So I still think that there are problems there. these are harder in AMR simulations compared to SPH. But for instance, with Gizmo, we have done simulations with the resolution of a couple of parsecs. So I think that they're, so dynamical friction operates on scales. So you need to resolve the sphere of influence around the black hole to be fully converged. So it's not perfect, but I think it's okay. Anything else? Okay. So let's move to tidal disruption events. If I don't finish the slides, it doesn't matter. I prefer you to have questions, and we have time to discuss if you want later. Okay, stellar accretion. As I said, this is a process, that we know exists in nature. We observe tidal disruption events. This was predicted initially by Martin Rees using mechanisms discussed by Hills. And it's simply that if a star gets close enough to a black hole, the tidal radius, the star gets stretched and accreted by the black hole. It's a complicated process. So it's not just that you eat part of the star, you form an unstable accretion disk. So I'm not going into the radiative processes here, but simply the idea is that if you have a star that gets close enough to the black hole, it becomes food for the black hole. The most typical approach is to use the so-called loss cone. In other words, if you have a black hole with this influence radius, this is the tidal radius, not the radius of influence. A star that is on a circular orbit will miss the black hole. A star that is on a radial orbit can catch it. The cone, defined by the ability to intersect the black hole's tidal radius, is called loss cone. It's the same that is important for other physical mechanisms like the shrinking of black hole boundaries, which I've not touched. You can ask me if you want. But so the typical way to estimate the rate of disruption or accretion of stars on a black hole is to simply calculate how many stars can fall into this loss cone. This is in 3Ds, of course. So it depends on the most important dependence is the distribution of stars, so the number density of stars near the black hole. So Stone and Metzger in 2016 did the first comprehensive work of trying to estimate the rates of accretion of stars on local galaxies. Again, there is a significant difference whether you have a nuclear star cluster or not. I'm not paid to advertise nuclear star clusters. It's really that they make a difference around black holes. As I said, the stellar density near the black holes on parsec scales is the most important parameter. So if you have or not a nuclear star cluster, so this overdensity makes a difference in the rates by 1 or 3 orders of magnitude. So this shows for a sample of local black holes the number of stars that are disrupted per year. Again, you see the difference between nuclear star clusters or not, but you see that overall the rate is about 10 to the minus 4 per year, meaning that one black hole is about a star every 10 to the 4 years. Yeah, let me keep this. So if you have 13 billion years, by how much you grow the black holes? Not that much. But this is a theoretical model by Markus Polkas in which he looks at the effect of accretion of stars over the lifetime of black holes all the way to redshift 0. This is the black hole mass, and this is the fraction of mass gained by different mechanisms. So this is the seed mass, well, whatever. Gas accretion is shown here in blue, and you see stellar accretion in pink. And you see that it can be a significant fraction of our low. Basically, if you have 10 to the minus 4 solar masses per year, you multiply by the age of the black hole, it's kind of 10 to the 5 solar masses in total. So if your black hole is small, this can be a significant fraction. If your black hole is 10 to the 8 solar masses, obviously this becomes a small correction. What is the main point that for high redshift, in my opinion, is important? is that when we look at the same, but only at high redshift, this is one simulation down to redshift 6 of black hole growth. So this is a mass as a function of time. This is the total mass of the black hole. This is what is accreted by gas that, again, at the end dominates in good agreement with this. This is accretion of stars. At the very beginning, when the black hole is small, accretion of stars can be important. And personally, I think it's one of these ways, it is one of the ways to possibly counteract these effects of AGN and supernova feedback that I mentioned. Because if you have feedback, meaning energy injection, you can affect gas, but you cannot displace stars. So star accretion will be some sort of baseline, not super high, but a baseline forever. Now, something that probably will not have time to discuss, so we'll say it now. As galaxies are more compact at high redshift, especially if you take the results for these little red dots, you can increase the stellar accretion rate to 10 to the minus 3, even 10 to the minus 2 per year in some cases. So then you have a lot of accretion just from stars alone. I'm not saying that this is a solution, I'm just mentioning this. So this is a bit of a summary. Gas accretion is expected to be the main growth channel. Sultan's argument, Eddington limit is not a limit. AGN feedback and supernova feedback, again, or more energy injection of AGN and supernovae explosions affect the growth of black holes. The level of this depends a little bit on when we turn from the physical process to feedback in simulations. Black hole mergers and stellar accretion may be helping in cases where black holes don't grow much. So this is something that applies to all black holes in the universe. I mean, here I really talked about 13 billion years of evolution. I want to say a few words about the effects specifically at high redshift. Actually, we have until noon, right? Yeah, okay. Let me go back to this picture, which is the birth of black holes. This I showed at the very end of my first PowerPoint. You have rare cases where you can form a single star, 10 to the 5 solar masses, and a single black hole. Everything is kind of spherical conditions. Then you can have these intermediate regimes where are getting closer to star clusters, where you have a distribution of black hole masses and star masses. And then you have POP3 stars, where you have, for the most part, low mass stars compared to the high mass ones. I mean, they may be more massive than today. And the question is, do black holes actually grow? At some point, they have to grow. But simulations consistently fail to grow black hole seeds. This is different from theoretical models, by the way. Theoretical models can make assumptions that are not affected by the hydrodynamics and the gravity that we see here. So this is, I just want to flash a couple of things. These are simulations by Sun-Myung Chon. I already mentioned his work. He really focused on what I did. I kind of tried to draw here. This is much nicer. So here, he literally looked at the formation of a possible supermassive star in a satellite galaxy into this main halo. He had a few of these candidates in his simulations, and then he simulated them, including growth on black holes. And if you start with 10 to the 5 solar masses, you end up with 10 to the 5 solar masses, unless you assume that there is no feedback, and then you get a few more. But in these conditions, so if you start from a very massive seed to start with, that requires these weird conditions of being satellite, having a lot of UV radiation, you are in the worst conditions ever to grow No, there are worse. POP3 stars is not. But in other words, it's not. I think that the title was something like the locations of black hole formation are really not conducive to black hole growth. And this becomes even worse if you include that radiation from black holes affects the surrounding. I mean, this was radiative feedback, meaning basically creating strong grand spheres around the black holes. If you have a strong grand sphere, the gas density, well, you have ionized gas. You don't have cold, dense gas can be accreted. So at the moment, simulations have mainly failed to grow black holes. You can get more favorable growth if the black hole is not placed in a satellite, but in a central galaxy. Then you have to think of a slightly different picture to form the black hole. But then you can have a little bit more growth there. In this case, AGN feedback is only X-rays, doesn't include UV radiation, so you don't have some, you have listened to Salim yesterday talking about the cross-section and X-ray radiation goes away, so it doesn't damage so much our environment. Anyway, my point is, I don't know. For low mass SIDS, the situation last year was terrible. People were saying, we don't grow light SIDS. So if I form a POP3 star with 100 solar masses, it will remain 100 solar, POP3 remnant will remain 100 solar mass until the end of the universe. And now they are, oh, well, now perhaps we have not considered all effects. Perhaps some of them grow. So just, I said, I put my notes from what I taught in February. I think that I have already seen papers between February and now that show different results. So basically, I would say we see black holes growing, so something must happen that we don't capture in our simulations, but I'm still a bit confused. Okay, for black hole growth, this is what I wanted to say. Before moving to the observables and just a global discussion, any questions on this specifically at high redshift? No? Okay. Actually, I want to take here a poll. Do you prefer to learn about how to model massive black hole observables, so the spectral energy distribution of black holes, or do you prefer to continue first on what we have discussed about this high redshift and the various questions and have a bit of global discussion altogether? Who prefers to learn about building SEDs? Okay. Who prefers to learn about what's going on about the high redshift crazy universe? Okay. Well, let's start with the latter, and then if we have time, we go to the SEDs. If you're interested in the SEDs, we can talk also a little bit later. Okay. So let me go back to what I said at the very beginning. Now you have information to actually decode why I was perplexed about some results and not others. The number density of black holes. We said pre-JWST observations were inconsistent with this population. And here, what you can show in a very simple way is that if black holes behave at high redshift as they behave today, same scaling relationship between black holes and galaxies, same Eddington ratio distribution, you can easily, so these are observations. This is a model that I developed in 2017 to explain, to predict the population at high redshift, which is not crazily away from what we actually see. So, although it treated quasars and AGN the same way. Now, a big change is, an important point is this type of empirical models is the starting point is the galaxy mass function. So here, this pink orange line is exactly the same as this gray line, but just changing the galaxy mass function. So this was done in 1 year ago. It's not so much ago. But at that time, I was using the first galaxy mass functions from JWST that were elevated. So anyway, point one, black holes don't live alone. If we want to understand black holes, we have to understand galaxies. Sorry, point two. Now, if we consider an elevated galaxy mass function, this orange line, we have plenty of space to reproduce all the black holes, all the AGN that we see in the universe. It's not something totally crazy. What is crazy? What is crazy is that you would predict a lot of quasars. If you extrapolate this, if you extrapolate this orange line, these are again the pre-JWST quasars. These are these crosses here. So you see that if we extrapolate in the quasar regime this orange curve, we would expect a couple of orders of magnitude more quasars. Observers assure me that there are no more UV bright quasars there, and I kind of trust them. So here we really have to understand, for instance, are the AGN really a different population, a different interracial distribution? This is something that could be possible, I mean, both in theoretical models, Raffaella Schneider and her group with CAT, and with observation, Ilan Maid and Jenny Green suggest that little red dots are characterized by super-Eddington accretion, or at least a different interracial distribution. But so that's why I mentioned that I really would like to understand if we're missing quasars at the high mass end. Quasars meaning high luminosity and not necessarily UV selected. But this is something that I think is important, like going to lower redshift. The overmassive black holes. I showed you this Lauer's bias that allows to accommodate the existence of overmassive black holes as those that we detect with an underlying population that is not overmassive. A very important point is that the results are strongly dependent on how you measure stellar masses. As I said, you have to include in the modeling all the selection criteria and all the uncertainties. So something that we often see in papers is that the stellar masses are quoted just with the statistical uncertainty, not including the systematic uncertainty in, for instance, star formation history. This is a big deal because if you change the uncertainty on the stellar mass from 1 dex to 0.5 dex, you change significantly the importance of Lauer's bias. So if we knew stellar masses perfectly, we would be able to decrease the uncertainty on the black hole stellar mass relationship. Same thing with the black hole masses. So yesterday, that's the question that I asked Roberto. Now we have things that push the black hole masses to lower values, the scaling relationship and these exponential wings, but also the stellar masses to lower values, these Balmer breaks. So it would be really nice to have a consistent analysis, including all these effects, so that these masses that were the observed masses, we could have a better understanding of where they sit. The growth of SIDS. And now here I will piggyback on Yoki's lecture. So I mentioned that supernova feedback suppresses black hole accretion in low-mass galaxies. That's when I showed you the gas mass being perturbed by supernova explosion. The actual effect is that black holes don't grow, so the relation, for instance, between black hole mass and stellar mass is kind of flattish up to the point in which the potential well is deep enough for the black holes to grow. So here the kind of red and yellow points are simulations, and blue points are observations. But this depends on how supernova feedback is implemented. Now, the strength of supernova feedback was not calibrated on black hole growth. It was calibrated to reproduce the galaxy mass function. And sometimes the efficiency is multiplied by a factor of 5 to take into account unresolved phases. And we always thought that we needed strong supernova feedback. Remember the picture of the very annoyed lady that both Yoki and I had. Well, I stole it from him. Our job was to reduce galaxy growth. Our job was to reduce black hole growth. But now we see a lot of massive galaxies with JWST. Have we tried too hard? So in fact, if the supernova feedback were decreasing efficiency, and this allows black holes to grow, then you have AGN feedback. Again, feedback is not physics, but you know what I mean. And in fact, Sophie Kudmani has shown that if you decrease supernova feedback and you let black holes grow more, then AGN feedback can have a role, although the effects are not fully identical. Super Eddington at the rescue. As I said, the last 2 years, Super Eddington has been the solution for everything. We grow black holes more, we don't see X-rays, everything. I mean, and then part of the guilty people. Both from the observational point of view, in principle, the large majority could be Super Eddington, just based on scaling relationship, changes in the scaling relationships, or on the, for instance, on the shape of the narrow lines. Not going into details, you can ask me more. Models predict a significant Super Eddington contribution. This is Trinity is an empirical model. I haven't talked about empirical models, but it's a type of models that in a Bayesian fashion put together lots of observational constraints to get constraints on the physical parameters. And here, if you are yellow, it means Super Eddington. So at high redshift, in low mass halos, you expect lots of Super Eddington. And the same is true for semi-analytical models. So is this the solution for everything? In simulations, we have consistently failed to grow black holes by Super Eddington. So CAT, what I showed here, is a semi-analytical model, meaning that, for instance, here you decide a time over which black holes are Super Eddington. In simulations, we let the Super Eddington evolution last as long as it can. And typically, so these are Super Eddington simulations by Alessandro Lupi. The growth of black holes is totally flat until it picks up. This totally flat, again, is this supernova effect. But then you have the growth of Super Eddington. But you see here, you have a blue line and a yellow and an orange line. These are both Super Eddington simulations. The only thing that changes there is the strength of the magnetic field, something that we don't know at all. Our resolution is parsec scales. The magnetic field is within the accretion disk, near the black hole. So perhaps it works, but I still don't know. And I will skip this. The mystery of the little dots, I already mentioned this, and the quasi-stars. So, I was quick, so I can talk about the SEDs after we discuss. So I still have these questions. Are all AGN candidates real AGN? And I think that this here, the key point is really Soltan's argument, the plot that I showed you from Inayoshi, in which we had this cumulative distribution going up and the high redshift that was higher than what you accumulate from redshift 5 to 2. To me, this is very bizarre. Are black hole mass estimates correct? If yes, we really need a lot of black hole growth that we struggle to have. Although, as I said, we calibrated our models not to have black hole growth, so we have to rethink this a little bit. And finding overmassive black holes is different from black holes are overmassive. So I will stop here a few minutes to see if you have any suggestions on how to tackle this, or if you have questions, we can discuss the questions as well. Yes?
I have a question about super-Eddington accretion. The fact that we don't see it in simulation could be the lack of known physics at the subgrid level. Like you said, the magnetic field has a lot of parameters.
Absolutely. Actually, what I think is most critical, at least from the numerical point of view, is that, well, two things. One is these GRMHD simulations, for the most part, predict the launch of these very powerful jets. However, when we look at super-Eddington AGN in the local universe, they're not all radio loud. So if we don't have these jets, actually, I had this note in the, yeah. If you don't have these jets, you don't have this problem of the duty cycle. Point one. Point two, with these jets, technically, your jet starts at the base of the jet is kind of a few Schwarzschild radii. And then it carves a hole and goes out. Simulations have a resolution of a couple of parsecs at least. So your jet starts bigger. So it has more impact just by this. So yes, there is, I'm totally open. To me, besides these numerical issues, what I've been mostly thinking about are these new simulations by Chris Fragile and collaborators in which, you have super-Eddington accretion at the edge of the disk, but at the inner part of the disk, you drop to Eddington, and then all the work is for nothing. If this is the case, it doesn't help a lot, or at all.
There is also the paper from Meyer group, I don't remember the name of the first author, Carl, Weibo, Carl, where they study the interaction of the spin of the black hole with the spin, the angular momentum of the disk,
Yeah.
and the angular momentum of the gas in it. But this is new.
Yeah, no, these simulations don't. But yeah, the spin evolution due to super-Eddington, true. So the jet power increases as you increase the spin. Blandfors-Nayak should decrease the spin, so decrease the effect of jets. But not at the level at which, so so basically you need weak jets. So if you use spins to kind of counterbalance for this, it can happen, but you really need to keep the black hole spin low for a very long time, which I don't think it's very easy to do. More thoughts? Yes?
I would like to question about what is the duration of the super-Eddington? Because I think it's not easy for a black hole to accrete, especially for have a continuous super-Eddington accretion.
Well, I don't know the answer. What I can tell you is what is the typical duration we see in simulations, which is typically rather short, but depending on the numerical implementations, usually it's shorter than 1 million year. But I would not take this as a number because it depends on how things are implemented.
So I would like to also question if the duration of the Eddington accretion is relatively short, is it enough for mass growth?
It is. It depends at which level and for which time scales. Because the combination of various super-Eddington events with sub-Eddington events in the end grows the black hole more than sub-Eddington events only. This was shown very nicely in the paper by Philip Husko. We also have something in the paper by Warren Massonneau. But again, what has been really bugging me in the last few years is all this mass loss. Because if Mitch Bigelman and Chris Fragile and collaborators are correct, then super-Eddington doesn't help at all. So I think that, before the numerics, I think I want to understand whether you have to go through the effort of doing this. Yes?
So also on the topic of the superenergy in combination with this observed X-ray weakness. So how does this exactly go together? So if you say that the superenergy could be like only in the higher and larger radii, so I know that the disk ground because probably it's also not really well known in the shape and but so are these so the only thing I always hear about this combination is that the condensed disk has to be very high. So in this large area is this
If I get to the SCDs, I will touch this. But so there are two different ways for super-Eddington to suppress X-ray feedback. I'm not going to touch. So one is in the extreme cases, you have a very almost spherical accretion disk with a small funnel at the top, so you don't form a corona, and so that's why you don't have X-rays. In the least extreme case, then you simply have lots of gas, so you have absorption of very dense gas very close to the black hole. And then there is Pierre-Madau's model that is too complicated for me to understand. So I hope that someone young and smart will explain it. But yeah, so there are various ways for which super-Eddington can lead to suppress X-ray emission. And they don't always all rely on the same picture, but it's always the effect of some dense gas that prevents either the propagation of photons or the formation of a corona.
But so how much effect is the orientation of the black hole in the observation of them? Because if we have this small funnel, okay, does it really mean we do not have a corona, or if we observe it from
Yeah. So in the small funnel case, this is actually, again, a model by Mitch Bigelman. Guess what? And actually, you're right. So if you have two extremes. Either you have no corona at all, and what you see is a kind of a black body with a temperature of 5,000, or you have only X-rays, very hard X-rays, depending partly on the orientation and partly on the thermalization in the disk. For the others, indeed, I mean, there is a paper by Fabio Pacucci in which he really looks at the inclination and the orientation. So this is on top of what I will show in a second, perhaps. Okay, so by the way, so what we were talking about was this. So typically, you have the accretion disk that emits, and then the photons from the disk are upscattered into this corona that is not a super well-defined object, but in which, are scattered in the corona. And in the corona, they are upscattered in energy, and they become X-rays. So to not have X-rays, one way is not to have the corona, and you can have that if the accretion disk has a very weird shape, for instance. Otherwise, you may have that clouds or winds within the accretion disk absorb part of these photons, and then it will be mainly a combination of how strong the winds are or the ejection with the orientation of the observer. But so typically, in the classic solution, the Shakura-Sunyaev solution, you have that photons are produced with a black body temperature that decreases as you go outwards, simply because the temperature is higher close to the black hole. So you have what is called a multicolor black body spectrum. An observer can see both radiation from the disk and from the corona if you have, and from the corona where you have the X-rays. Now, how clear is this? So this is a very nice theoretical picture. Shakur-Sunyaev, 1973. But then if we actually try to produce AGN SEDs, this is a very nice analysis done by Chris Richardson, in which he compared 3 different theoretical models for AGN SEDs. This is just continuum, no emission. I'm not going to talk about lines, by the way. They're all normalized to the same luminosity, but you see that the actual emission at different frequencies is significantly different. So you still have to choose. But if you choose, you can either choose to have a self-consistent first principle model. For instance, Chris Dunn has worked significantly on that, and her models are publicly available in XSpec, which is an X-ray analysis package, but you can get the spectral energy distribution from there. Observers usually prefer to just use a combination of power laws, shown here, for instance, in green. These are power laws trying to reproduce the typical spectral energy distribution of quasars and AGN. Option 3, and this is what is shown here, for instance, with cloudy or disk power law or my other work, is to assume a functional form and then tune the free parameters to obtain something that in the limit of the observations gives the same result. It's your choice. As far as I know, there is no consistent solution yet. When we go to super Eddington disks, now if you go back to the 60s, it's actually quite interesting to look at all the history here. When I was working on this in 2015, I found 2 families of models, those predicting lots of X-rays and those predicting no X-rays, those predicting lots of UV photons and those predicting no UV photons. So if there is uncertainty in thin disks for sub-Eddington sources, it's much more uncertain at super Eddington. So we have this radiation trapping. The paper Bigelman 79 is where you see all the physics. But the bottom line is that what you should expect based on these first principles is that you have a thin disk in the outer edge and a puffed up disk in the center that absorbs part of the radiation. Chris Dunn has actually developed, Segras and collaborators, so with Kubota in particular, has developed a full model. But before that, it's called AGN Slim. So here you can compare the sub-Eddington cases with the super Eddington one. So the sub-Eddington SEDs are in gray, the super Eddington are in various colors. And here, the model takes into account the changes in the accretion disk. Another option is if you are as lazy as me, you just change the SED a little bit, or you take into account this trapping radiation. Personally, I think that AGN Slim is the best bet that we have. Again, considering that it's not a given. But at least it's self-consistent. Radio emission is theoretically, how to get the radio emission from an AGN based on what we produce in theoretical models, which is the mass and accretion rate, and the spin, if you're lucky. You cannot predict the radio emission from first principles, mainly because you need at the very least a magnetic field. So there is a paper by Jeff Bicknell in 2018 giving at least a baseline, and then you can use some simplified approaches. But I think that this is also, we were talking about radio also yesterday with Salim. This is something that we really need to do a little bit more. And just to give an example here, the uncertainties on the radioluminosity function, whether it is as close as all AGN, or all galaxies host a radio AGN, or very few galaxies do, are still there. But I really want to suggest reading papers by Ghiseline and collaborators about the observability of radio AGN at high redshift. Because of the high temperature of the CMB, the production of radio lobes is suppressed. So you would still see only compact radio sources, not the large ones. I just want to show this. Besides this, we have to include obscuration and attenuation. You can do it in two different ways. One is to extrapolate from observations. This is a paper by Andrea Merloni, where it shows the obscured fraction as a function of redshift and luminosity. What we typically do is just to apply this as a correction to the fraction of observable AGN, or way that all you can use it for the distribution of column densities. With simulations now, we can actually track the distribution of dense gas in galaxies, and so we can use a different approach. So if you're using a simulation, you can have a self-consistent approach to model galaxies and AGN. And I think I have a few things on LISA, but I think I prefer to have some questions from you and show some cool LISA stuff only if you ask. Yes?
So you just talked about modeling the SED in X-ray and radio.
Yeah.
How does, but you were also mentioning the models predicting UV radiation load. So is this predominantly in lines? Or?
No. So the models that were not predicting UV, these were all developed in the 60s and 70s. So different. So it was really about the history of the evolution. Honestly, still. So at the moment, if you can do two things. If you want to really start from first principles, either models like Chris done. So you take radiation processes, temperature, densities, and you calculate what you get. Or you post-process a GRMHD simulation. Now there are also simulations with relative transfer. And you actually calculate the emission that you have there. Now, there you have the emission at thousands Forshee radii. So you don't really know what comes out. But I would say that now there is consensus. So if I go back to Chris Richardson, so this slide, I think that there is an overall consensus of what the shape is. You have a big blue bump. You have an X-ray tail. In classic Shakura-Sonaev solution, the position of the peak temperature decreases with increasing black hole mass and with decreasing Eddington ratio. So you should have, for instance, that low mass black holes are bluer. This is kind of, yes, seen, but not. So there is a paper, on the SDSS quasars. Actually, they've done this analysis. So they see hints of this. No. I would say that there is still a bit of a disconnection between first principle and what is seen. I don't know if this answers your question or not.
Okay, so I guess the UV part is not so clear, or clearly also modeled.
I would say that the UV part is typical, especially for bright quasars, is where all the models are anchored. So, for instance, AGN, QSO AGN does a very good job at reproducing the X-ray luminosity given the UV luminosity. I'm not sure about the opposite, but this is true. Yes? No, I said that models of quasi-stars predict a black body spectrum, which is not a great fit for, which is not a great fit for what is actually observed. So there is it's the opposite. It's not a perfect match. Although Mitch says that, I think he says that pretty much it works. But if you talk to Ron, Naidu, I think it here, what observers and what theorists think has good fit, I think it's the actual point. Anything else? So perhaps we can finish early.
Up to you. You have 5 minutes if you want to use them.
I don't know. I feel that the people deserve 5 extra minutes of rest after this. So I will stop here.